a new chapter on Monday. So you have a new pre-lecture available today, due before class on Monday. Another thing, a couple of people have had issues reaching me on email. In general, if you do not hear from me within 2 to 3 days of sending me an email, that means I have not gotten it or forgotten about it. Most likely not gotten it, so just resend or talk to me. Okay, my average response time is between 2 to 3 days for fixing whatever the issue is. Okay, so let's get your clickers set to the class that started and make sure you're on a roam so you don't get kicked out. And we'll start where we stopped. So on Monday we basically discussed vectors and we started projectiles. So the whole idea of the projectile is it's two-dimensional motion. Right? You have the vertical axis and you have the horizontal axis. Typical projectile is something that is acted on only by gravity. Right? So when it's in flight, so to speak, the only force acting on it is the force of gravity. Right? And we treat projectile motion just like we treat all two-dimensional motion problems. Essentially a combination of two separate one-dimensional problems. Right? So from last week, you know how to handle one-dimensional problems. Right? You have the kinematic equations that give you what happens to displacement, velocity, and acceleration along a straight line, whether that straight line is horizontal or vertical. Right? And then we also studied vectors, right? Remember all that fun geometry? And the whole idea with vectors is simply to be able to take those one-dimensional vectors that you get, right? Velocity, to the, displacement, and acceleration along an axis, and combine it with the other axis, the perpendicular axis, right? So velocity, acceleration, and displacement along the other axis, right? So if you have components of a vector, you can get back the full vector. Okay. Right, and this is kind of the question we stopped on. I don't know why this squeaks. It's really not my voice. Okay, so from the same height, at the same time, one ball is dropped, another ball is fired horizontally. Which one will hit the ground first? Good, that is appropriate. They both hit the ground around the same time. And the reasoning is quite straightforward, right? As far as the y-axis is concerned, the vertical axis, right? Both of them start with zero initial velocity, because one ball is fired horizontally, which means zero in the vertical, and the other is just drop, which means zero in every axis, right? So both of them start with a zero vertical velocity, and they fall the same distance under the influence of gravity, right? So they land at the same time. Right? The displacement in the y-axis, the acceleration in the y-axis, and the initial velocity in the y-axis are all the same. Right? So t, when you solve for the kinematic equation, it's almost just raw stuff. Right? T is the same. The next question, of course, is the one where you guys may have adjusted your answer last time. Okay, I'm going to close this, so if you haven't click in, please. Right. So they both hit around the same time, and then there's this one. So you have a red ball, a yellow ball, and now I'm asking for speed. Right? So combine this with the previous question. Right? In this case, the yellow ball is fired horizontally, the red one is dropped. Right? And I'm asking which one is moving faster when it hits the ground. So moving faster just means I'm asking for speed. Right? Whichever one has the highest speed. There's multiple ways to actually answer this. You guys know that they land at the same time, right? You just did. Okay? It's pretty clear that the path taken by the yellow ball is longer than the path taken by the red ball. Right? When you're looking for speed, the average speed is total distance over total line. So the yellow ball is moving faster. It covers a greater distance in the same amount of time. right? That's the magnitude of its speed. Correct? Like that's how fast it's moving. The yellow ball, when it lands, has two velocity components, right? It has a vertical velocity vector, which is the same as the red ones. Right? In the y-axis, they're moving at the same speed when they hit. Right? But the red one is also moving in the x-axis. Right? So it has an x component of velocity and a y component of velocity, which you have to add together and get the magnitude. Right? And you add a dx and a dy by summing the squares and taking the square root by adding. Right? Those are your two vector components, you're getting your full vector back. Right? Since the red one only has one component, which is equal to the component of the yellow one. Right? So the yellow one has that additional component. It has a greater magnitude of velocity. Everyone with me so far? Okay. Right, so click something if you haven't yet. Let's, yeah, that's the correct answer. So yellow, stop, and there we go. Okay, I'm going to need a volunteer, someone who can catch the ball and is not going to make me look terrible. Go for it. You're right there. Okay, you're not focusing on her catching the ball, you're focusing on the trajectory of the ball. The trajectory is the path, right? All I'm going to do is launch the ball at an angle towards her, right? And she's going to catch it. There we go, see? All the ball did was went up, came down in the vertical axis. And what did it do horizontally? Did it speed up, slow down, or just move with constant velocity? Great, okay, thanks. So, in the x-axis, there is no force acting on a projectile, right? Gravity acts in the vertical or the y-axis, right? There is no reason for the ball to slow down on the x-axis if you're going to get it specifically on, right? So the whole concept of a projectile is that you have motion on the y-axis, which is motion under the action of gravity. The ball goes up and down, or something is going straight down. Right? And as it goes down, it speeds up under the action of acceleration of gravity. And as far as the x-axis is concerned, it's simply motion at constant speed in the x-axis. But there's no acceleration in the x. Right, before we actually go on to find some math, a couple of questions. So if I were to toss the ball straight up, right? So I'm standing around, I toss the ball straight up, so I'm giving it a vertical velocity. Right? And I walk away from under it, what will happen to the ball? Anyone? I toss the ball straight up and then start walking. Will I be able to catch the ball? No, right? Can try. This is not me having forehand-eye coordination in the morning. Right? But if I walk after I throw the ball, I don't catch it. Did everyone see that? Okay, now let's see if I toss the ball while I'm walking, what should happen? If I toss it straight up, I'm not tossing it like this, I'm tossing it up. Right? While, will I be able to catch it? Yes or no? Why? Right, because when I'm walking, right, as I'm walking forward, as I'm walking, right, this ball has a horizontal component. Correct? So if I walk and I toss at the same time, right, when it leaves my hand, it has a vertical component, which I just gave it, right, and it has the horizontal component, right, and it has the same horizontal component as me, right? So the ball will always be right above my head if I'm walking with it. Does that make sense? Right? It's the same thing as if you're traveling in a train, right, at constant speed, and you toss something up. It's going to land in your hand if you toss it straight up. Right? But to someone outside that train, looking at you for whatever reason, tossing something up in your comfortable chair, it's going to look like that thing you tossed followed what kind of path? What does it look like? A parabola, right? The same thing as me just tossing the ball at someone else. Right? It looks like that from the outside. Does this make sense? Right? So all we're saying is that the horizontal and the vertical components of motion, right, can be dealt with separately. Right? We can literally break up motions into motions along straight lines which are perpendicular to each other. Right? And that's how we deal with two-dimensional and three-dimensional motion. Okay, we always reduce it to one-dimensional motion along each axis. Right? And then deal with the eventual problem at the end. Okay, combining with that. Right? Remember, the only thing common to all of them, like all the axes, will be time. Right? The amount of time moved in one axis is the same as the amount of time moved in some other axis. Right? Okay. Now the promised math. So this is a ball hit with a velocity, with some initial velocity, at an angle of 55 degrees. Right? So in this case, that's the trajectory of the ball. We all agree. Right? This velocity vector, this initial velocity vector, does it lie on the x-axis, y-axis, or both? Lies on both, right? It's making an angle to the x-axis, 55 degrees. Right? Which means it has a component along the x-axis and a component along the y-axis. Everyone agree with that? Okay. So if I'm going to start separating stuff, right? Like my vector quantities are displacement, velocity, and acceleration, right? Those are the ones I separate for the x-axis and the y-axis. So when I start separating the initial velocity, right? Like what's the initial velocity of the x and what's the initial velocity of the y? I look at my initial velocity vector and I have to resolve it. Right? I have to put it into its x component and y component. So that circular stuff from Monday, that's what we use it for. Right? We're splitting up that initial velocity vector, which lies along both the x-axis and the y-axis, into a vx and a vy. Okay. Right. So again, the process is fairly straightforward. After you read the question a couple of times, draw a diagram, label all quantities. So in this case, we know that the initial velocity is 15 meters per second, and the angle it's launched at is 55 degrees with respect to the positive x-axis. I've called r the horizontal distance traveled. That's typically called the range of the projectile. That's what the r stands for. It's like how far along the x-axis does it move. Okay, we're asked two questions. How long is it in the air, and how far does it travel? So, our first step, right, is to split that velocity vector. Right? I have three vector quantities to deal with. Displacement, which at least in the beginning, this was displacement in the x and y axis. Right? Velocity, that's my initial velocity, and acceleration, which I don't. Okay? So, split the vector. So, draw it separately on an xy coordinate. Right? We know V0 has a magnitude of 15 meters per second. Right? So, that means the size of this vector, right, this length, is 15 meters per second. And this theta is 55 degrees, according to my question. Right? The side adjacent to the angle will be the cosine. Right? So Vx initial is V0 cosine theta, and Vy initial is V0 sine theta. Everyone following this step? Right? All we're doing is saying that since the initial velocity vector doesn't lie purely in the x or purely in the y, I have to find out how much of it lies in the x and how much of it lies in the y. Right? And in order to do that, I sadly need to. Okay. The horizontal component comes out to to be v0 cosine theta. The vertical one is v0 sine theta. And so now we have initial velocities in the x and y axis. Right? You can check your numbers. And at that point, we can start breaking this problem up. Right? So let's first look at the x-axis. Right? So what we know about the x-axis is that there is no acceleration in the x, the horizontal x. Right? When we get the x-axis, the projectile is something that's acted on purely by gravity, which is a little. Okay, so there is no acceleration in the x-axis. And no acceleration means what must be happening to velocity? It's constant. Right? Not the total velocity of the projectile, right? Not the full velocity, just the x velocity. Right? Just the x component of velocity is constant. Does this make sense? Because the acceleration in the x is zero. Okay? So any projectile can be treated as just moving in a straight line with a constant speed without changing direction. Right? So if I label the velocity vectors, those blue lines, right, my horizontal component of velocity doesn't change at any point during this flight. Right? Okay. Why we're still on this? A common conclusion is because of the y-axis, a lot of people think it's going to stop at the top. It's not, right? It will always have an x component of velocity at the top of the flow. Right? So any projectile is moving slopes where? At the very top. It's moving its slopes, right? It only has an x slope. Right? Everywhere else you have an x and a y. And the x is the same. Does this make sense? Okay, where is it move fastest? Where you launch, right? Or where it lands, like right before it lands, or right when you launch, right? It's moving with the same speed at both positions. Okay? Right. So we know that there is constant velocity in the x. Now, Vy, right? This is purely the y-axis. And if you look at what Vy does, it's just, okay, that's a typo. Velocity is changing in the y direction, not the x. And it looks like this. Right? Those red lines represent what's happening to the velocity in the vertical axis. Right? Which should make sense. Right? It gets smaller as we go up, which means the object is slowing down as it goes up. Right? And then those lines get larger as they come down, which means it's speeding up as it goes. Right? And that should be familiar. That is a board or stop, and it's coming down. Everyone with me? Okay. So we've essentially broken projectile motion into going up and coming down and moving horizontally at a constant speed simultaneously. Okay, so that's the actual velocities, both of them, right, in the x and the y. So let's it's that straightforward. Those are my two one-dimensional problems. Okay? And now you make a table of quantities that you know and quantities that you do not know. So in the y direction, I know my initial velocity is 12.3 meters per second, and that came from resolving the velocity vector. Right? I resolved the initial velocity vector. So my initial component of velocity in the y direction is the y component of that initial velocity. Right? That's how much of that speed is going to be upwards when the ball is going. Okay? So in terms of like just going up and down, that is the speed with which we're going down. Everyone with me? Okay. At that point, over here, y0 and y final are listed as 0. 0, which should make sense. It's a projectile that went up, came down. Right? So displacement in the y-axis is 0. Does that make sense? The displacement in the y-axis is 0. Right? It's the same thing if I toss a ball up and I catch it on the when it comes back down. If I look at the total displacement during that motion, it's 0. Right? It's back where it stopped. Correct? So in the y-axis, it's displacement is 0. Right? Which is not very helpful for finding height, as we saw last time. Right? You should still break up the motion to be. Right? If I want to find how high something goes, I consider half the motion. Does that make sense? Okay. But as far as what we know and what we're putting on that table, we're going to leave that there for now. Okay. I can solve for t, which is my unknown. This makes sense? Right? I have an initial y-axis. I have an initial displacement, a final displacement. I have the initial velocity in the y. I have the acceleration in the y. I solve it. Right? This is giving me time of flight. Everyone with me? If I'm not interested in how high this goes, it's giving me time. Right? That was the question. How long is it in the air? Do I need to double this time? Why not? He said no, he's right. Martin White is right. Why don't I need to double this time? Because it's the full motion. I put the displacement as 0. Right? The initial position and final position are 0, which is the full motion. Does everyone agree? Right? If I had broken it up such that I was considering just the time to go up, then I was double. Right? Because it takes the same amount of time to come back down. But I did not break it up. Right? Simply because the question didn't ask about. Everyone with me? Okay, so it's a simple one-dimensional problem in the y-axis, and that gives me the time of flight. And this is something that will be true in general for all projectiles. Like, conceptually, if I were to ask you what determines how long a projectile is in the air, what should the answer be? What thing do you control that determines how long a projectile is in the air? You control the velocity, right? And you're controlling the velocity, you're controlling the magnitude and the energy. Correct? In general, you should know this, right? The longer, the time of flight of this projectile is set by how long it takes this ball to go up and down. Right? In the x-axis, there's no acceleration. The only reason it stops moving in the x-axis is because it came down in the y. Everyone follow? So what determines time of flight is the initial velocity in the y-axis. Right? The greater that is, the longer this thing is in the air. It should make sense, right? The faster stuff is moving upwards, right? That's what determines how long stuff is going to stay in the air. Okay? Right, now let's do the x-axis because we were also asked for range. In the x-axis, I know my initial velocity is the x component of v0, which was 8.6. I know the time because I solved it in the y-axis. Right, it's the same amount of time in both axes. My initial displacement in the x is 0. I'm looking for final displacement. And it says A is a question mark, but we know A in the x is 0. Right? So look at those two values of A, in the x and the y. For any projectile motion problem, those will be your values for A. If gravity is the only thing acting on this projectile, right? Acceleration in the y is g downwards. And acceleration in the x is 0. Okay. So I'm looking for x. I know I'm moving with a speed of 8.6 for 2.5 seconds with no acceleration. So I literally just multiply the speed and time. Right? That's how far I went. And I get a final x position of 21.5 meters. That's the range. Right? That's how far this ball goes in the x-axis. Okay, so I know that's a busy slide, but that's your recipe for solving projectile motion problems. Right? Separate the vectors into the x and y axis, and then deal with them as separate one-dimensional problems. Right? Do not mix them. Like, what that means is do not use velocity in the y-axis in an equation with acceleration in the x. Okay, the more common one is people use acceleration in the x and also 9.8. That's not true. Right? Acceleration in the y is 9.8. Acceleration in the x is 0. Okay, remember diagrams, labels, tables. That will get you really far. Okay, and like I said, start with the vertical motion because that is what determines how long this thing is in the air. Okay, before we get to that, so far we've dealt with motion along straight lines, and this whole process has been about combining motion along straight lines to give you a representation of motion in 2 dimensions and generalize it to 3 dimensions. Correct? We considered stuff basically going in straight lines, right, along an x-axis or a y-axis. There is one other thing that you can do in a plane, which is of course go in a circle, right, round a curve. Okay, so any curve can be thought of as part of a circle. Everyone agree? Okay. So if you're going to talk about moving in a circle, we're still going to talk about velocities and acceleration of this object moving in a circle. Now, tell me this, if you're moving in a circle with constant speed, are you accelerating? Yes. Right? And the reason is because while you're moving in that circle at constant speed, velocity is changing. Right? Not magnitude. The magnitude of velocity is speed. Right? And as you said that one, you can literally take a circle with constant speed. Right? I mean, I've done that. Not walking, but by driving. Correct? Okay. Velocity is still changing. It means I'm still accelerating. So everyone follow that. Okay. Now think about what must be the direction of that acceleration. So remember this, we started this like last week. If I have an object moving this way, so velocity is in that direction and A is in that direction, what happens to this object? If velocity and acceleration point in the same direction, what happens to velocity? Theta. If velocity and acceleration point in opposite directions, what happens to the speed? So I just said that this thing is moving at constant speed in the circle, right? Which means A cannot be pointing along it or against it, right? Because it's not speeding up or slowing down. This makes sense, right? So A must be pointing perpendicular. This makes sense to everyone, right? So think about like something is moving that way. I want it to move this way. Right? I'm going to have to push perpendicular to the speed. This makes sense to everyone. Right? In order to turn this thing in a circle, I'm always pushing perpendicular to the velocity. Everyone follow? So the acceleration must be perpendicular to the velocity. Everyone good so far? Okay. Right. So this is a ball. It's literally a piece of sponge tied to a string. So even if it flies off, it's not going to hurt anyone, I believe. Right. So it's really not very heavy. Why is this thing going in a circle? It's kind of interesting, but yeah. Why is it going in a circle? towards my hand at every single point in its motion, right? And my hand is the center of this circle. Does that make sense? Right? If the string were to break, like at some point in its motion, I'm going to draw that. This is a ball. No, this is the ball being whirled in a circle of radius r. Right? That's the string. If this string breaks at this point, what does this ball do? Does it do this, this, or this? A, B, or C? B. Everyone agree? Right? If the string breaks, it continues with its speed v in a straight line. Correct? It flies off tangent to the circle. Right? So v at every point, right, the velocity of that ball at every point is tangent to that circle. Right? And in order for this thing to be moving in a circle, the acceleration has to be pointing towards the center of that circle. Does this make sense? Okay. Right, so that tells me the direction of this A, which is responsible for turning it, right? Now we need to come to magnitude of it. So far we dealt with A's that speed up objects or slow them down, right? So it's delta V over delta T, and that delta V I can find using numbers, right? Because V actually changed, right? The magnitude of speed, magnitude of velocity changed, right? In a circle, moving at constant speed, the magnitude of velocity is not changed. Right? So if I try doing delta V over delta T and just doing numbers, I'm going to have an issue, correct? Right? I'm saying it's accelerating and I calculate delta V over delta T, that's it. Right? Both are simultaneously true. Okay? There is a kind of acceleration that's responsible for an object moving in a circle at a constant speed. And the next step is for us to figure out how do we determine the magnitude of that acceleration. Okay? For that, I am going to do a bunch of drawing, and you are going to try and follow along. Okay, so this is an object moving in a circle, right? The circle has a radius r. The object is moving with a constant speed v, right? And at every point in this circle, v is tangent to the circle. We all agree so far? Right. So now, if I draw another circle, right, the radius of which is v. Okay, so like over here, v is pointing in that direction, right? So I'm going to start my new circle, which has a radius of v, right? It's an arrow pointing upwards. It has a certain magnitude, which is fixed. It's constant speed. Everyone agree? Okay. As this ball travels this circle, right, at different points, v is pointing like this. We all agree? Correct? Okay. If I put those V's over here, as this object moves in a circle, the velocity vectors do this. Does this make sense? Right? You can imagine a circle of velocity vectors. While this object is moving in a circle, the velocity vectors are doing this. Everyone agree? Okay. Now let's put some A's down. So just like V is the rate of change of displacement, A is defined as the rate of change of velocity. Correct? So in this circle, I know that A points inwards, right? From V at all points. Because we just said that, right? A has to be perpendicular to V to move it in a circle. This makes sense? Right. Now consider my velocity circle. Right? This guy. Right? A in this points like this. Still perpendicular to V. Everyone follow? What's common to these two circles, of course, is time. Right? The amount of time taken by a ball to go through one complete revolution, right, is the same as circles to complete one revolution. Everyone follow me? Okay. So, since this is constant speed, right, I can write the total the speed here, v, is the total distance, which is 2 pi times the radius, right, the circumference of the circle, divided by the time taken. Does everyone agree? Right? It's an object moving at a constant speed in a circle of radius r. Right? So the total distance traveled in one complete revolution is 2 pi, the circumference. So the speed is the circumference divided by the time. Okay. And now we do that for my velocity circle. Right? The radius of this circle is v. Right? So the circumference of this circle is 2 pi v. Right? And that divided by t is the rate of change of velocity. So that's a. Does this make sense? They're relating the same quantities similarly. Right? Because v is rate of displacement over time and a is rate of velocity over time, they relate this way. Right? So remove t, so you can write t as 2 pi r over v, and you can write t as 2 pi v over a. Equate these two, you get 2 pi r over v equals 2 pi v over a. Divide out the 2 pi's, you get a is equal to v squared over r. Okay, caveat, I do not expect you guys to derive this. Okay, what I do want you to do is focus on what this is. Right? This is called centripetal acceleration. Right? The term centripetal literally means center point. Okay, this is the acceleration responsible for moving in a circle of radius r with speed v. Right? So any time an object undergoes a change in direction, right, it's undergoing centripetal acceleration because it's moving in some arc of radius r with speed v. This makes sense? And notice the fun thing about it. This is non-zero even if v doesn't change. Right? An object can be moving at a constant speed. Right? V is non-changing. And as long as it's moving in a certain radius r, it has a non-zero acceleration. Right? The other accelerations that we've been dealing with, if delta v was zero, they are zero. Right? Like your linear accelerations, if the speed along the axis is not changing, right, then the acceleration in that axis is zero. Right? Over here, what we're saying is that even if the speed isn't changing, because direction is changing, acceleration is non-zero. This makes sense? And look at how it depends. So now we can go back to the slides. So it's directed towards the center, and look at how it depends on v and r. This is, remember I told you an excellent drive. So think about that, right? You're rounding a curve of radius r. A nice gentle curve versus a sharp curve. What's the difference in r? A large r, does it represent a gentle curve or a sharp curve? A gentle, right? A large radius of curvature implies the curve is slow. Right? And as most people who drive know, it's much easier to drive at a higher speed on a slow curve. Correct? Right? So, if you look at the expression, it's telling you it's inversely proportional to r. The larger r is, the slower the curve is, the less acceleration you need to go up with the same speed. To round it. Does this make sense? You have a sharp curve, r is small. So you need a larger value of acceleration. Right? And it's directly proportional to v. So the faster you're going, the more acceleration you need to be able to round that curve. Everyone with me? Right. So you have no excuses for not being able to round curves anymore. At least while riding. Okay. Um, so there's basically two types of accelerations that we need to worry about. Okay, when an object is moving in a circle. If it's moving at a constant speed in a circle, there is no tangential acceleration. Okay, it's only centrifugal acceleration. Tangential acceleration is stuff we'll deal with later if we need to, but just as an FYI, all it means is that stuff can speed up and slow down while you're in a circle. Right? You can press gas while you're rounding a curve. Correct? And as you do that, you're providing tangential acceleration. Like you're changing the speed with which you're moving around that way. So at that point, you need two kinds of acceleration. Tangential to change the speed, and you still need centrifugal to move in a circle. Okay. Right, now let's do one quick problem. This is back to projectiles. Right, so you have a diver who runs horizontally off a 30-meter high cliff with an initial velocity of 4 meters per second. You're asked to draw his trajectory, you're asked how long does it take him to reach the water below, how far away from the base of the cliff, and the fun one is with what speed does he hit the water? So let's hope we get to number 4. Right, so it's a 30-meter high cliff. I don't know if this is a diver or someone not very happy in life. Sorry, I was meant to be inside voice. Okay, so this is my diver running horizontally off the cliff. Everyone with me so far? Okay, he ran horizontally off the cliff, which was 30 meters high, right? So I have some initial velocity v0, which is given to me to be 4 meters per second. And the first part of the question says draw his trajectory, which means draw the path he takes. What does that look like? A parabola, right? So it looks like this, right? That is his trajectory. It's a nice parabola. Okay. How long does it take him to reach the water below? Okay, so before we get to the actual numerical ones, what's my next step? I have a diagram and labeled some stuff. What should I be doing next? Before I get to the initial planning, what should I really do? This is a two-dimensional problem. Make a table, break stuff into components, if I can. So, I make an x-axis and a y-axis, right? I'm going to start measuring from here. So this is my x0 equals 0, and this is my y0 equals 0. Okay? I'm free to choose my conventions, right? I'm free to choose my conventions, so I'm going to pick that direction as positive x and downwards as positive y. Okay? I can pick upwards as positive y, I'm just choosing to pick downwards. Everyone with me? Okay, so my initial position in the x-axis is 0. My final position in the x-axis is unknown. I do not know how far from the base of the cliff he lands. Right? I'll call that r, and it's an unknown. My initial velocity in the x, by the way, I'm putting initial velocity and final velocity in the x there, but it's the x-axis. So what do I know about the velocities in the x? It's constant. Right? Whatever velocity it started with in the x is the velocity for the keep in the x. There is no acceleration in the x-axis. Right? For a projectile. So I don't need to write v0x and v0y, I can just write vx. And do I know vx? Do I know from the question the initial velocity in the x-axis? It's 4 meters per second. right? That's the part about him diving out horizontally, right? So horizontal is the x-axis, and all of that 4 meters per second is in the x-axis, right? So that goes there, and similarly, x is 0. Okay, I do not know t. Now, do the same thing for the y. Y initial is 0, y final is 30 meters. V initial in the y, V final in the y. What is my initial velocity in the y-axis? 0, right? Because he jumped horizontal. Right? If he made an angle with the x-axis while jumping, I need to resolve that initial velocity and find the initial velocity with the y-axis. Right? In this case, it just so happens that his initial velocity was completely along this. Right? So there's nothing in the y. So 0. I do not know my final velocity in the y-axis. Now, remember, I'm saying I don't know this. Don't say it's 0, because that's after his motion. That's after he hits the water and stuff has slowed him down for whatever reason. Right? The actual, when we say final velocities, we're talking about right before he hits the ground. Okay, like with what velocity does he hit the ground? Okay, and AY and T. What is AY? You said negative 9.8. Is that correct? Positive 9.8 because I took that whole point. Right? Remember, it's a convention. Right? Acceleration due to gravity is 9.8 downwards. If I said downwards is positive, acceleration due to gravity is plus 9.8 meters per second squared. Okay? And downwards is my positive direction. I've gone from 0 meters to 30 meters in the downward direction. Right? So this is 9.8 meters per second squared, and t is unknown. Everyone following me so far? Okay, at this point, if I want to figure out how long does it take him to reach the water below, which axis should I focus on? The y-axis, right? That's what determines how long it's going to take him to reach the water below. And for the y-axis, this is a simple problem. It's something being dropped with 0 initial velocity to a height of 30 meters. Right? So I can use y final equals y initial plus v0 y times t plus 1/2 ay t squared, right? To figure out the time. This is 30, this is 0, this guy is 0, so 0 times t is 0, plus 1/2 9.8 t squared, right? So you have 60 divided by 9.8 equals t squared, so t is approximately the square root of 6 seconds. Right? Don't worry about the math, but does everyone follow this? Right? You can find time simply from the y-axis. Okay? Once you have time, how far away from the base of the cliff is he when he hits the water? Right? That is the x-axis. I now know t is square root of 6 seconds. The distance traveled in the x is vx times t. Right? There's no acceleration, so distance is speed times time. Okay, I'm going to stop here. We will find the final velocity on Monday. As an FYI, starting